What we have been doing up to now is studying what's called the human model processor, or the model human processor, which explains what happens inside a human being as a reaction to seeing and thinking about an interface change. And the goal from all of this exercise is to understand the human capabilities and the human kind of reaction to any change in an interface, so that you can design better interfaces. So as you see, we are actually building stuff from the ground up. We started with some physiology of the eye, and then we moved to the brain, and now we're going more towards cognition after covering the perception part. So today we'll talk about how humans think or react, and what helps them to think and react to an interface. So let's start that. And this is really the block in the middle that I have highlighted here in red, which is the cognition part. Last lecture we went into a detailed discussion of the gestalts, why they are important, how can you design an interface to invoke a gestalt in the human brain. And today we're going to kind of tie the pieces with what we have discussed before with cognition, how humans think. Now, as I mentioned, there is a whole area in psychology called cognitive psychology, and what cognitive psychologists do is the study of the mind, the brain, not the anatomical study, the fact that we have lobes or we have neurons, as much as how humans think, how they store information, how the information is connected, and how we can understand why humans react to certain conditions in a certain way. Now, this turns out to be very important for us when we design interfaces, because whether you're designing an e-commerce website or a desktop application, you have to invoke kind of the right circuitry in the human mind, and for that you need to understand how it initially works. Okay. Now, cognitive psychology is one of the probably the oldest field in psychology, if you'd like, and there's lots of things to learn from them, but I'm not going to cover everything because that will require a whole course. I will cover the basic things related to learning processes and information related to memory, attention, and reasoning. Okay, and also we will cover the important topic of language. So this is what we're going to study. We will learn a bit about memory, we will learn about the chunking theory, how do we think, we will learn about a number of principles. I've listed them, 3 of them here, and we'll also learn about Hicks' law and a few more things, which is conceptual models and attention. Now let's start with memory. Okay, what is memory? Human memory is very similar to computer memory. In fact, I should reverse my statement. Computer memory is very similar or modeled after human memory. Even though those who designed computers and designed specifically RAM, the random access memory, they didn't really understand the human memory then, because that was like back in the 1940s and 50s, and we had limited information at that point about the structure of human memory. And it turns out that many years later on, once brain studies and brain machines like EEG machines, the one I described to you earlier in 2 lectures from this lecture, turns out that actually the human memory is actually very, very similar to the computer memory in how it works. It's built or encoded in a way to establish connections between neurons, and whenever there is a connection, that's a 1, that's a logical 1, and whenever there is no connection, that's a logical 0. So at the lowest level, a computer memory is nothing but a reincarnation of the human memory. Okay, so just like computer memory uses 1s and 0s, human memory would use 1s and 0s. Now in the human memory, the 1s and 0s are made to make up meanings, things like letters, numbers, symbols, words. Okay, they are made up of 1s and 0s, and I think that should be amazing by itself. The fact that our brain memory storage is similar to how we store information inside a computer, which means that whoever invented the computer many years back was really not really inventing anything new, because this is actually how we work. Okay. Now, connecting neurons establishes memory. So what we think of as a logical one is a pair of neurons connected. Remember, when I talked about the brain, I said the brain is made up of billions of neurons, and on average there is 10,000 connections between coming out from a neuron connecting to neighboring neurons. So whenever two of these touch, then we have an activation, and that activation is the equivalent of one in the computer memory. Okay? Now we have network of localities, if you'd like, in our human memory, and the connections compose a massive network. So you have learned many years back when you were young that there is something called door. The door is this piece of wood that exists in the hole somewhere in your room that takes you outside from the room, or you can close it to have the room closed, or you'll be sitting alone. The concept of a door is stored in your memory as neuron connections, and it is tied to usages of doors. So doors are gap filling, doors are for opening and closing, doors are for protection. Okay, door in your room acts somewhat similar to the door in your car. So this is also encoded in your memory. So the word, you can imagine that the word door is connected to other concepts through neuron connections. And when you're actually trying to remember something from your memory, you're trying to activate it. And activating it means kind of lighting on this little circuit that represents the concept of a door, or that represent the concept of Newton laws of motion, or that represent the concept of an accounting balance sheet or income statement. Okay, so the concepts are not connected in an arbitrary way. The relation between the concepts is also encoded, or is basically neuron connections, and you establish these connections when you learn. So you've learned the functionality of a door many years back, and that's why when you've seen a car door, you will not surprise. You can open it and go inside, because you open your room door and go inside. Okay, so the functionality is associated with the object, as we say. Okay, when you try to remember something, you're trying to activate a piece of your memory. Okay, and that activation is what represents what we call meaning to you. Okay, this is a door, it's not a basket, for example. Okay, now because a neuron is participates, or a network or a concept network participates in many other concepts. For example, the door is connected to the concept of opening and closing, and it's connected to the door of being inside the room, or it's connected to the concept of being part of a car. When you try to remember something, you have to activate exactly the right set of connections. Okay, and when you try to remember something, you might be remembering things that you don't need to remember, and that means false activation, that you've activated or switched on a part of your memory that actually you're not really searching for that, you were searching for something else, but because they are similar, you activated both. Okay, or you activated one and didn't activate the other, or you really want that the stuff or the concept or the meaning that you didn't actually activate. Now, so this is the first thing you need to learn about memory. Now, the other thing you need to learn about memory is that we have two types of memory. We have the long-term memory and we have the short-term memory. Now, in the long-term memory, it actually has a very interesting capacity that has not been completely discovered or documented, but we know that it has huge capacity, and it varies from one human being to the other, but we're really talking about a massive storage capacity. Okay, perhaps one day they will figure out that it's equivalent to maybe 2 terabytes or 10 terabytes. We don't really know, but it has massive capacity, and people have shown to memorize and store in the memory quite significant amounts of information. What you store in your memory are facts, procedures that you learn. What you also store in your memory are skills, and anything you learn as a skill, including playing sports, driving a car, and so on, or designing a piece of software, or coding, which is also a skill, partly a skill, you will store it in your long-term memory. Okay? Now, a property of long-term memory is that it has little decay, which means the information stays there for extended periods of time. Another property of long-term memory is that it has an approximately 100 milliseconds access time. In order to remember anything, you need about that much time from your, in order to remember something from your long-term memory, you need about that much time. It has also this very interesting property that is fast to read from and slow to write. Why? Because we think that the long-term memory connections are actually quite strong. And because they are quite strong, it's hard to establish them. How do you actually establish writing to your long-term memory? You do that using a process called elaborative rehearsal, which is a fancy name for saying repeat, 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 repeat. Now remember, from your school days, if you'd like to memorize something, you'll keep repeating it, okay? Now, why are you repeating it? The repetition creates the neuron connections between the memory parts, okay? If you're actually into memorizing Quran, for example, they would tell you that you have to revise your memorization every once in a while to avoid forgetting. The same thing if you're into memorizing poetry, for example, or you're trying to memorize poetry, you'll be told that you have to keep repeating until it becomes really embedded in your memory, okay? What that really means is the elaborative rehearsal or the repetition is the key to establishing these strong bonds, neural connections in your long-term memory. Now, the other type of memory, which is the short-term memory, is quite different. Well, first of all, this is what you use to hold what we call intermediate products of thought. So while you're actually undergoing any mental effort, you're thinking about what you're doing, and the information that you're thinking of is held in the short-term memory, not in the long-term memory. And it has a fast decay rate, okay? It varies from between one human and another, but it's between 5 to 226 seconds. So on average, really for most humans, it's about 7 seconds. So anything you put in your short-term memory will not stay after 7 seconds, it will just evaporate, okay? Now, when you're actually reading anything or you're thinking about something and you're trying to study a textbook even, you have to go from the short-term memory to the long-term memory. So it's like a temporary storage that you put the information in before pushing it into the long-term memory, okay? Now, obviously, if you maintain a rehearsal process along the way while you're actually looking at a piece of information, at least you can keep it in your short-term memory. That's what's called maintenance rehearsal, okay? So you're maintaining it in your short-term memory, because without the rehearsal, without the repetition, it will evaporate from your short-term memory, okay? So this is different from elaborative rehearsal. Elaborative rehearsal takes much longer, way more effort from your side to be able to push the information from the short-term memory to stick in the long-term memory, okay? Now, one thing we know, and this will have an implication later on user interface design, is that whenever you are thinking of any topic, as I mentioned, you're using your short-term memory. If you interfere in the user flow of work or thinking process, then the information tends to evaporate faster from the user brain, the user short-term memory, okay? So we will come to a conclusion later on when we talk about this, is that we should not interfere the user while they are doing the main task of an interface, okay? Now, why? Because you're interrupting short-term memory. You're not interrupting necessarily his thinking, you're interrupting the amount of time it takes, or you're decreasing the amount of time a piece of information would stay in the short-term memory, which is irritating to the user, because the user suddenly thinks that his thinking has just stopped. The interruption comes because the short-term memory content has been erased by the interference that you made. So there's nothing to think of because there's nothing in the short-term memory in the first place, okay? So short-term memory is the victim of any kind of interference that you cause to the user. And a consequence of this as well, we will see later on, is that when you design an interface, you understand the main task and you allocate the biggest portion of the screen to the main task and put everything to the side to avoid, again, interfering the user. So, here is the takeaway. When you interrupt the user to display a message or alert while working on a task, the user tends to forget what he was working on. The longer the interruption, the more he forgets, and the message is, don't interrupt the user. In fact, nowadays, Windows come with a mode of no interrupt. So you can actually switch it on if you're working on a project or writing a piece of paper, a research paper or a thesis, or writing a project document, to avoid interruptions from main interruption sources like Facebook and Twitter and so on. And it was introduced in Windows specifically, and very recently, actually, in the last few years, just to avoid this problem, which is that interference destroy the user mental process. They just stop thinking. Okay, and this is something we should avoid in a user interface. So basically, the message here, displaying messages to the user, is not a good idea. Okay, let the user seek the information. Now let's talk about some cognitive theories. The first thing we're going to talk about is called the chunking theory. Now, it turns out that when we divide a piece of information into smaller pieces, the user is able to comprehend it better because he's able to store it better in his short-term memory. Okay? So as I write here, chunking, a process by which individual pieces of information are bound together into a meaningful whole. Now, our short-term memory is best suited to 7 plus or minus 2 chunks, which means from 5 to 9. More than 9 chunks, you are bound to see some memory lapses, that the user will not really remember what they were looking at, okay? Even within a short duration afterwards. You can see this applied in many concepts, or in many designs, or in many interfaces. For example, when you ask the user to input his phone number, don't ask him to input it as one whole big number, but chunk it into 3 pieces, like what I have put at the bottom here of the slide. Similarly, if you ask the user to remember anything, split it into 3 pieces or more, depending on the length of the text. And again, the reason behind this is chunking. Another example we see in Egypt, historically the car plates used to be made up of numbers. So the policeman who would be standing in the street when a car breaks a light is supposed to write the number. But when you look at the number and you got 7 digits, it's very hard for the policeman to actually remember that. Okay? The longer the number, the worse, obviously. If you go into a 13 or 12 or 11, all of them are really bad or really hard to remember. So recently, the government here followed, recently I mean in the last 10 years, the government followed the international convention, which is to split the car plate numbers into 2 pieces, one made up of 3 letters and the other one made up of 3 digits. And this is much easier. First of all, they've introduced chunking, and then they've avoided repetition by mixing letters and digits. Okay, so this is an example again of chunking. In this case, actually, they are helping the policeman standing in the street, or the traffic guy standing in the street, to take your number when you break the light. So obviously, if you do that a lot, probably your interest would be to keep the old style. Now here is an example of chunking in HCI. Okay, now this is a form that takes the user information, and whenever we ask the user to input a piece of information, we should try to use chunking as much as we can. Okay, so you can see that in the phone number entry, where the number is split into pieces, there is the city code or state code at the beginning, and then followed by the number divided into pieces. The same thing you see it in the birthday. We don't ask him just to input a sequence of digits, but we separate it by slashes, so the chunking is effective, basically. Okay, that he can look at the numbers he is typing, and he will recognize, okay, this is the number of the month, this is the number of the day, and this is the year. Now, here is an example of what not to do. Okay, if you look at this one, this screen, horrible screen, and the reason why it's horrible screen, it's overloaded with information, and there is no place you can do chunking here. Okay, remember, to think and comprehend anything you look at, it has to go through your short-term memory. Okay, so the best thing to understand this is if you remember from your computer hardware courses, there is something in the feature in the CPU called the cache, and the cache is basically a memory that exists inside the CPU. Okay, so this is apart from the RAM, and anything the CPU works on, any computations the CPU is supposed to do, will do it on the data in the cache. So the information is retrieved on the bus from the RAM and put in the cache for the CPU to work. Your short-term memory is basically the cache. You have to have the information there to be able to process it by your brain. Okay, you don't have a CPU in your brain, you have the brain itself, the frontal lobe. So the problem that exists here, when you look at this interface and you're just amazed by the number of details you have to pay attention to, is related to the fact that you're overloading your short-term memory. Your short-term memory works best with 7 plus or minus 2 chunks. There's no chunking here, okay? You're trying to process the whole thing in one shot. So your brain is overloaded with the amount of information presented, okay? And once you look to any specific component of this interface and you understand it, and then you go to other components, you will forget what you actually understood from that component. So you will go back to it and try to understand it, okay? That's if you keep looking at it and try to even understand it. So the takeaway, always chunk the information presented to the user and chunk the entries the user needs to fill, okay? Chunking is a golden rule that we always try to apply. Now let's go to thinking. So now you understand a bit about memory and why do we need to do chunking and the importance of that, okay? And also the importance of avoiding interruption. Now let's go to the big thing, thinking. How do you think? Now, thinking is nothing but a spreading of activation. It's like your brain is like a circuit, and when you activate part of it, you use it, okay? Now, when you activate a part, you have no control in exactly how the activation will proceed. You can stop the activation, but as long as you want to activate, neighboring or adjacent areas will also activate, okay? It's like a connected network. If you go into one piece of the network and you provide power to one of the machines, as if this power will travel, or the excess power will travel to neighboring machines. So you start somewhere and all the neighboring circuits will be activated upon your activation of a specific location, okay? Now, this, what we call chain of activation, is influenced by a number of things. First of all, the location of the initial activation. Where are you activating in your memory? Which detail, okay? What are you trying to remember? Second, the strength of association between concepts, okay? The association between a room door and a car door is not very strong. Both of them are doors, you will understand that, but why would you think of a car door when you start thinking about a room door, okay? Not really that related, so the sense of association might be a little bit weak, okay? Now, the other one is the radius of activation. What are you searching for? If you're searching for a piece of information, you're not really aware of the details of it, you will try to activate subconsciously as many pieces in your brain as possible that will help you to do the recall, okay? Now, whatever you activate, you start thinking of. We say you're thinking now because you're activating different pieces of your memory, okay? The memory storage itself is different from the frontal lobe. They're two different things, but whatever you process in your frontal lobe is the result of the activation. So we tend to describe the thinking in terms of the activation because you think of what you activate. You're not going to think of what you don't activate, okay? Now, we come to the incredibly important topic of language usage, okay? Now, here is the story behind this. For many, many years, in fact for generations, the researchers within the social science area by the name of linguistics, which is the study of human language, were divided into two groups. According to the following question: do humans think using language or they think using some other abstraction? And because it's very unethical to do intrusive experiments in human brains, you're not allowed to get someone and open his brain and do an experiment on his brain. You can do that with a chicken or a rat, but you shouldn't do that with a human being, hopefully. Now, the problem is it's actually difficult to study the human from the outside. So they used to conduct experiments, all kind of experiments, trying to answer this question. For linguistics, this is very important because all what they do is the study of language. So they wanted to answer this very basic question, and also cognitive psychologists were very interested in it. Do humans think using words or think using something else? Now, nowadays, the battle has been settled. We know that we think using words. And that has amazing implications in social sciences, okay? Why? Because it turns out that the quality of your thinking and the quality of your understanding of a problem is related to the words being used. So again, the quality of your thinking is related to the words being used, the words that you use to think of the problem. And the quality of your understanding is related to what you read in words of the problem in front of you, or of the message in front of you in general. Now, why is that a big issue? Because it has two aspects. Well, actually, it has like a huge list of aspects, but I'm just going to focus on two things. The user interface part, which is when you display a message to the user, you have to use proper language. And proper language means correct language. So if you're displaying a message in English, you have to use proper English. The words are used correctly, in the right order, and without slang. Okay? Now, why that is important? Okay, let's start the story from the beginning. Here is the story. Language exists for us to communicate. Because humans are intelligent, they have refined the languages they use. For most cases, especially for languages that are popular and that have been around for a while. Okay, if you think of a language that exists in a local tribe or within or used by a local tribe somewhere in Polynesia, for example, well, okay, probably the language is a little bit limited. But if you think of languages that has been around for hundreds and hundreds of years, or maybe thousands of years, and still being used, and there's a huge population using it, the language has been refined to describe everything accurately. So the quality of your thinking is related to what words exist in your brain, because you think in words. And any message you read, you will make sense of it based on the words that is used in the message. So let's say you go to a bank machine and you're withdrawing money, or you're transferring money. Let's say transferring money to someone from a bank machine, from an ATM machine. So you go in, you put your username or your card, and then you put your password, and then you specify the phone number of the person you would like to transfer the money to, and then you specify the amount, and you click OK, and then the message that you get back from the ATM, cool. What does cool means? Okay, cool means it's cool. It means maybe it was transferred. Okay, it means you're good. Maybe you're a nice person. Okay, it means anything or nothing. And this is the problem with using slang. Accurate formal or formal languages are accurate because they are meant to be used in a detailed way, in the sense that we have so many words for so many situations to be able to accurately describe what we want to describe. Colloquial language in all languages are abbreviated versions of the language where few words are overloaded with meaning. For example, in Egypt we have the word ishta. Okay, now ishta means it's a product of milk. Ishta means you're excited. Ishta means I'm not going to do it. Okay, ishta means forget it. Okay, and ishta means it's done. So the use of the word ishta in an interface will not really communicate anything to the user that is meaningful. It will communicate many meanings. One of them is probably what the user wants, and other ones are not related. Okay, and the user will not be able to understand which one you mean. So generally, the use of colloquial language in an interface, whether it's English or Arabic or Chinese or in any language, is not acceptable. Remember, an interface is just the facade of a piece of software that's supposed to be doing functionality to enhance people's lives, or perhaps even to save people's lives, or to make people's lives better. So there is a legal side to software. If you display the wrong message to the user and the user makes the wrong decision, you could be counted liable for the message that you have displayed. So the general message here is that you don't use colloquial language, because colloquial language in an interface is an absolute a mystery in many cases. Okay, and this is not just for Arabic, this is for all languages, and this is the message here. Now there is another message which I mentioned. There are 2 points to this. The more words you know, the better your thinking is, and this has a lot of implications in social sciences and political sciences as well, because it's not about being of a higher IQ. Okay, it's not related to IQ directly, but the more words you know, the better the quality of your thinking. Okay? So let's reverse that. The less words you know, the worse the quality of your thinking. Okay? And one of the challenges in user interface development, which words to use. So what most software companies do is they try to resort to words that are not going to be ambiguous, that are not colloquial, and they are acceptable by most people. But then you run into a trouble, and this is really a debatable issue. You run into a trouble is that your bag of words that you use in an interface is quite limited. Okay? Now, obviously, this will vary from one culture to another. This is something you have to be careful of. For example, if you look at English, there are about 400,000 English words. What a typical British, if you think of Britain being, the language of English, what a typical British guy would use or girl would use throughout their life is just between 4,000 and 5,000 words. So most interfaces are going to draw words from that 4,000 or 5,000 words that are being used. But English has 400,000 words. Okay? So this always opened the debate, should software use or software interfaces use more accurate words? Okay, it's actually better. Now, the same thing also we have in Arabic. Arabic have, because of this routing system that exists in the Arabic grammar, we have way more words than in English. We have, some people claim it's more than 1 million, and some people claim it's way even more than that. Okay, but if you actually look at the number of words that we use in day-to-day basis, okay, it's actually going to be much less than even English. It's going to be in the realm of being 1,000 or less. Okay, which complicates things, because if you would like to describe things accurately, you need the right words. If people are not trained to use the right words, you run into trouble. Okay, because the words are there, but people are not using them. Okay, so it has implications beyond HCI, of course, but I don't want to go into non-HCI stuff. But if you just keep thinking about it, then you could draw a lot of very interesting observations about things you see around you. And this is again to stress the point, the quality of thinking depends on accuracy of understanding, which depends on accuracy and clarity of message to the user. Okay? So don't use words that are colloquial, and don't use technical jargon, by the way, okay? Because this is another very important aspect to all of this, that you don't display a message to the user showing that you know technical stuff. You display a message to the user that he can understand. Okay, let's look at this one. If you're not a computer scientist and you've seen any one of those messages, what would you really understand? Pretty much nothing. Look at the one at the bottom right. Wrong button. This button does not work. Solution, try another. Another what? Okay, you have to be accurate and specific. Okay. Or the one in the middle up, the operation failed, an object could not be found. Which object? And you have to understand, this is a user that might not have seen or learned anything about object-oriented programming. So the notion of an object, what do you mean by an object here? Okay. So, the nice thing is, by 2020, many of these really bad messages are disappearing from software because people are learning that you're not supposed to display such messages, okay? But you still face other challenges with messages. For example, when you are building an app for Android, you have a very limited screen real estate. How would you display a meaningful message in such a small space? Okay, so you still run into trouble, and you have to understand what the user will be thinking of the words that he's reading for you to communicate the right meaning. So the message here is that, or the takeaway, messages displayed to the user should be precise, accurate, and in proper formal language. Okay. Now, some of you might feel that a language like Arabic, the formal version of it is actually quite heavy, and that's your own personal subjective opinion. What is important is that you avoid the legal liability by displaying messages that are colloquial and consequently will mean many things at the same time. Okay. Words like ishta, words like halawa, words like معلش, words like ما فيش مشاكل, okay? The words that could mean something and the opposite are not formal language. the message you display to the user has to be a reaction to what he did, and it has to mention what he did, and that what he did is either successful or not. Like for example, تمت إضافة المنتج إلى قائمة الشراء. Okay, you might tell me like, this sounds like heavy. This is not what we talk. I don't care what you talk. I care that the user, when he reads it, he gets the point. And in any language, you will definitely get the point if you use the formal language. Okay, at least for languages that have alphabets, like English, French, German, Arabic, and so on. Okay, Chinese and other Korean, other languages, Japanese have another story. So I'm not going to go there. But the point is, with languages that have alphabets, and they have been around for enough time, okay, the formality ensures understandability. Informality and colloquial stuff is for the market. This is actually why, by the way, it's called colloquial. In Arabic, it's called سوقية, and سوقية is coming from سوق, and سوق is the market. And the reason why these words are used in the market, because they enable fast transactions. Let's imagine you're going to buy 2 kilos of banana. You're not going to stand in front of the guy and tell him بكم هذه, and then you will actually try to fix your grammar and your نحو while you're talking. You say بكم and he say 2, or he say 2. Okay, the speed by which a transaction is conducted in the market is what, not just in Arabic, by the way, in all languages, it actually what generates colloquial usages, because merchants in the market are trying to execute transactions very fast, and that's why colloquial appears everywhere. Okay, but if you're talking about legal liability, stick to proper language. Now let's move on. This is my rant about languages. Now let's move on. We will look at a number of theories that are very important in actually building an interface. The first one is going to be called the encoding specificity principle. Okay, this says that the memory is better when the context available at encoding is also available at retrieval. Okay, you see, when you store information in your brain, you store it as a network of concepts. We call that encoding. Now, there is the main concept, perhaps it's in the center of the network of your storage, and there are related around it concepts, and they all together go into your memory. Now, we will call this kind of, if you think of it as a circle, what exists on the perimeter of the circle is the context, okay? And what exists in the center of the circle is what you're really trying to push into your memory. Now, if this same set of concepts that exist on the perimeter are available for you when you're trying to do the retrieval, you will activate exactly the right part of the circle the right part of your memory that you're interested to activate. Okay? This will include everything that was available to you, to your perception, when you're doing the encoding or when you're doing the storage. This includes the time, the mood, the sounds, everything in the environment. Okay? Now, if you cannot remember, so let me try to put it with an example here. If you think there's a circle, and inside it there is one piece of information, and on the perimeter there are other 5 pieces of information. Okay? Now, if you're trying to remember what's inside the center of the circle, the best thing to do is to remember everything that was in the perimeter as well. Okay? Because they're all tied together as one network. The more you activate, or the more that you do pattern matching with more components to match, the faster you will activate the right circuit, or the right network, or the right subnetwork in your memory. Now, if you have only in front of you, or presented to you, or using your own attempt without anything presented to you, if you just have 2 of these out of the 5 that exist on the perimeter, let's call them queues. If you have only 2 of these queues instead of 5, it will take you longer time compared to if you have 4 of these queues out of 5, okay, to remember everything. So this is what I say here. You will forget because of too few or ineffective retrieval queues. So if you try to remember something and it is in your memory, but you're not able to remember it, okay, then it's because you don't have enough queues to do the activation. Okay, you're not capable of switching on the right part in your memory that will make you remember. Because once you switch the right thing, that will be what your cognitive abilities work on, what your frontal lobe will work on. But if you can't switch it on, there's nothing to work on, there's nothing to think of, okay? So you say you forgot, okay? So the thing here, the key word here is the context. The more the context is available, the better or the faster the retrieval, okay? And this is what the encoding specificity is telling us. Now there is another related principle which is called the discrimination principle. It says that recall is determined by the candidates that exist in their long-term memory relative to the cues. So if you have too few cues, you cannot remember, and if you have too many cues or candidates, you will get false memory. Okay? Now, why does this exist as a concept? Because remember, all the concepts in your memory are linked together in a massive network. Everything is linked to everything in somehow. Okay? So when you were young, you learned about the room door, and then when you went outside, and the first ever time you went with your parents in a car, someone must have mentioned the word door, like close the car door, or maybe your mother is telling your father, make sure that the door lock is closed. So you will record that this is actually a door. So the concept of a room door will be somehow tied to the concept of, or using neurons, to the concept of a car door, okay? So when you're activating a subnetwork, if you have enough cues, you will activate the right one. If you have less cues, you will activate all the ones that have the cue that you're thinking of, okay? Now, so you're discriminating between subnetworks based on the number of cues, okay? And if you're not able to discriminate, you will remember lots of stuff that are not related, because you're basically going through them trying to figure out which one is the correct one you're looking for, okay? That's why we say if you have too many candidates or too many cues, you will get false memory. You will be trying to remember something, and then you remember something else that is completely unrelated, at least from your logical point of view. But the reason why you remembered it is because you started to think or to search in your memory using a cue that was involved as part of that subnetwork that you suddenly now remember, but you realize now that you don't need that one, okay? So it must be that there is a cue there that you were thinking of or trying to use as a key to actually retrieve the right or access the right subnetwork. Now, here is an example of using encoding specificity and discrimination principles in HCI. In any e-commerce website, you have a list of historical transactions the user has made, okay? Before websites, and before e-commerce, and before the internet, when people used to track the history of transactions, they used to track it using the transaction ID, which is the unique number that was given to this specific transaction. But that's the worst thing you can do, actually, because the transaction ID has no significance to the user. In fact, he might not have even stored it in his brain. So with the advance of the internet, and people are interested in building better interfaces and more usable interfaces, people started to fall back to psychology, and specifically to cognitive psychology, to understand how do we help people recognize among previous transactions what is the best interface to display basically previous transactions, okay? And what I describe here has application beyond previous transactions, but at least it becomes very clear with previous transactions. Okay, so the transaction ID, as you see, is not even displayed here, okay, because it has no meaning to the user. What is displayed here are cues that the user would have stored in his brain when he was doing each one of those four transactions. So the date is important, but actually, if you look at this specific example, it's even better to omit it because all of them are in the same date. Okay. This will not help discrimination because it's the same piece of information in the four subnetworks in the user brain, where you have one subnetwork for each one of those transactions. Now, a difference appears in the second column, the type. You have payment from and payment to. So if you're looking through your history, your memory of transactions, what you will be looking for, perhaps is a payment you sent to someone, not a payment you received from someone. Okay, so this is the second column has a queue that could be used. Okay, although the discrimination is not high because 3 of them are payment from and only 1 is payment to. Okay, now the third one is actually very important, the name of the person whom you did the transaction with, or who the user did the transaction with, because every entry has a different name. So this will be a queue that will activate a specific subnetwork in the user brain. The status, not that important. The detail, it's just for you to see more details related to this transaction. And perhaps the last column is also very important, which is the amount, because each of the amounts are different from each other. So if you go to your transaction, even though you have like hundreds of transactions and you're looking for the details, perhaps you would like to print one specific transaction, what you would remember to try to kind of isolate it from, identify it from the list of transactions displayed on the screen is whom did you do the transaction with and what was the amount for. So out of these, the really important ones is the name and email and the gross amount, which is if this represents what the amount of money you've been sending or receiving, because this is PayPal, this will be the right column to display. Okay, detail you need because you got to go and navigate to the rest of the details of the transaction. Status is not terribly important, it could be omitted. Type, yeah, it is somewhat useful. Date is completely useless here. If all the transactions were done in the same day, then you can simply omit it. Okay. So this is how you actually use these concepts in an interface design. So the takeaway is, when displaying history of previous performed actions, show the user all the details associated with each action to be able to distinguish between them. Okay. Otherwise, don't include it. And this actually makes a difference for you if you're designing an interface on cell phones, because the screen real estate is really small. So this is actually one takeaway that might help you to decide on the best information to display on the screen. Now, the third principle we're going to cover is called the uncertainty principle. And in this principle, it simply says that the decision time increases with the level of uncertainty. Okay? The more options you have, and the more you're uncertain about them, the more time it takes you. Okay? Now, a very related law to this is called Hicks law. Okay? This actually tells you the average amount of time it takes a user to make a decision given a number of choices. Okay? Provided that, this is very, very important, provided that the chance of picking any choice is the same as the chance of picking any other choice. Okay? Now, let me give you an example just to understand what do I mean by that. Let's say you decide to go out to have dinner, and you go to a restaurant. Now, you don't have preferences regarding what to eat. So you grab the menu and you start reading it. Now, if the menu has 10 pages, perhaps you read it in 2 minutes. If the menu has 50 pages, you will read it in way more than 2 minutes. Okay? So if you don't have bias towards a specific choice and you're just browsing through the menu, going back and forth, the more choices you have, the more time it's going to take you to decide what to eat. Okay? But if you made your mind, even before going to the restaurant, I'm going to go to this restaurant and I'm going to eat pizza because that's the best thing they make. So when you open the menu, you're not really looking for a choice. Okay? You just perhaps would like to check the price, or maybe to check what add-ons you can add to the pizza, but you're not really going for other items. Okay? What this law is about, if you don't have bias, if you don't have a preconceived intention about what actually you're going to pick. Okay? And that's why it says given unequally probable choices. Now, what the law tells you is the average amount of time it's going to take any user, given any number of choices, provided that they're all equally probable, the average amount of time it's going to take for the user to actually make a decision. Okay? The formula is simple. N is the number of choices, and B is a constant that is experimentally driven. Okay? So that will give you just approximately how long the user is going to wait before making a decision. The implication of this on user interfaces is that don't give lots of choices at any one point to the user. Okay? always restrict your choices to the bare minimum, okay? Because it overload the user. Remember, the user notice when he's actually overthinking or spending time doing an additional effort of thinking just because the interface is complex. So you always want to present a simple interface so the user doesn't feel that he's required to do excessive thinking to make a choice. This is an example of an interface where you don't even need to know Higgs law to feel that, okay, there is something wrong with this interface. There's so many tabs, okay? What you're asking the user to make a choice here, okay? Which tab to go and click on to further, check the interface components that he needs to set up. And obviously, it's just going to take him a lot of time to go through all of these back and forth until he figures out which one to pick, okay? This is what we should try to avoid in building an interface. Now let me show you what you can imitate in building an interface. This is PayPal new interface. Historically, when you logged into PayPal, you would not see something as simple as this. You would see like a lot of subsections or divs in the HTML, with lots of functionality, available to you to click on. Okay, and you would see news, and you would see your history, and all kind of stuff. They removed everything, and they present the user with just 4 basic choices. Okay, pay for goods or services, send money, request money from someone, or create an invoice. When you go inside each one of those, you will see another screen that looks like this with more options, and then you will click again to see another screen that looks like this that will have even more options. So the functionality is still there. PayPal has lots of functionality, but it has been redesigned so that a single screen only has 4 options, okay? And it's as simple as what you see here, and this is exactly what you should be designing. Simplicity here is key, and hiding the details also is an important thing. That you don't present the user with lots of options because you think, he might need to do that. Yeah, sure, he will need to do that, but you don't have to actually display everything in front of him right away, okay? For example, when I click on request money, there will be so many details, okay, involved here. Or when I click send money to friends or family, so many details involved here. But I don't need to see everything in one shot, okay? And again, the beauty of this interface is that the user takes like almost nothing, just a few hundreds of milliseconds to click on the right icon he would like to proceed with. Okay, so the takeaway: do not overwhelm the user with options. Try to reduce the options presented in an interface. Now we come to the also very important theory or cognitive principle called conceptual models. Okay, now this is actually how we store information in our brain. Okay, now we have these models in our brain, and this is what I have been describing earlier, that our network of storage consists of subnetworks, and these subnetworks are linked. And now all these subnetworks are make what we call models in the brain. Okay, that's called conceptual models or cognitive models. Okay, now so let me read the second point. It says a conceptual model is a description of the proposed system in terms of a set of integrated ideas and concepts about what it should do, behave, and look like, that will be understood by the users in the manner intended. The really important part here is the in the manner intended. Okay, now everything you store in your brain will ultimately at a higher level represent some conceptual model. For example, you learned when you were very young that there is something called the remote control. Perhaps you had a DVD player at home or a TV, and your parents taught you how to use a remote control. It wasn't just any remote control, it was a DVD remote control or a TV remote control. But if you noticed, all remote controls are very similar, or to a great degree they are actually quite similar. And there is a reason why product designers would always stick to the standard kind of layout of a remote control. For example, you would always see the power button at the top left or top right, and it's colored in red. Okay, what actually has happened when you start to learn how to use a remote control, you've built in your brain a conceptual model of a remote control. A remote control is a device that is used to control remotely another device, and it has basic functionality, which is switching it off, switching it on, mute, a set of numbers So you have a panel that consists of buttons, and the buttons are labeled with numbers, and perhaps you have another panel that has the alphabetical letters, and in the middle you would have a circle that you can use to go right or left, or you will have buttons to the right and left of the circle, and the circle has the word OK. I mean, almost all remote controls in the world more or less look like this, okay? So even though you have never worked with a projector remote control, if I give you a projector remote control, you will have a glance at it and you will immediately be able to actually use it. But how come you've never used the projector remote control? What actually has just happened is that you have activated your brain, the subnetwork that represents the conceptual model of a remote control. And once you see a remote control, you know how to use it because you are actually relying on previously stored information about the conceptual model of remote controls. Okay? Now, so conceptual models are important. Why? Because if we can activate the right conceptual model in the user brain, the learnability of the software is going to drop to zero. He's not going to actually be needing to learn the software. He will just use it without learning, and that's a great idea. You know, that's a great advantage to our software we can add. If the user can just look at the software and figure it out, okay, this is how it works, then there's no learning. He doesn't have to go and take a course in Udemy to actually know how to learn your software, to learn how to use your software. Okay. Now, so the user conceptual model of what is he seeing. There is what he's seeing, which is the interface, and there is the conceptual model in his brain that gets activated when he sees the interface. Okay. The trick is to activate the right conceptual model, okay? And it has to be very clear in the sense that don't mislead him, don't trick him, don't make him tired in trying to understand how this works. Make the jump from the interface to the conceptual model straightforward, as simple, as fast as possible, because this way actually the user is satisfied. He feels actually that he's not going to waste his time trying to learn your software. What that really means is you should not innovate in a way in the software that makes it hard for the user to understand. Okay? Don't break the expected look and feel of the app or of the interface because you're just trying to be innovative. Okay? Because what you're really doing is you're not making use of the user stored conceptual models, and we want to make use of them. Okay? So for example, if you're building an Android app, the user has a certain concept of how an Android app look like. Okay, there is the drawer, you pull it from the top or from the side depending on the Android version, and you get the options to configure the application. Okay, don't try to innovate there and tell me, okay, I'm going to make him hold the phone, flip it up 2 times, and then push it to the front, push it to the back, and then he will get the settings screen. This is crazy. Okay, you follow the standard, you follow the conceptual model of an Android app to enable the user to use your app as fast as possible. Okay, and that will not be really innovation in what I just described. So when it comes to conceptual models, there are really 2 types of conceptual models in your brain: activity focused and object focused. And you are all the time throughout your life, whenever you come through a conceptual model based on activity or based on object, you will actually store it and you will tend to use it later on. Okay, so we have a number of activities or activity-based conceptual models that will be stored in your brain. There is the conceptual model of instructing, that the user instruct the system to do something. Okay, and this is most suitable, and users like to use it when the task is repetitive. Okay, especially if it's based on multiple objects. Okay, so you would code the interface, or you would build the interface so that as if the user is instructing the system. So for example, in an ATM machine, the user could be withdrawing money, and he will do that several times. So you write the verb of in the statement or in the message or in the options that the user is seeing with a verb. You start with a verb like withdraw money. Okay, it's like the user is instructing the ATM machine withdraw money, as if he's telling it withdraw money. Okay, or transfer funds. Okay, so he's instructing the ATM machine to do that. Okay, this is a conceptual model the user understands. He has been trained since his childhood that he could be placed in a situation where he tells someone do something, or perhaps he has seen it in the movie if he hasn't done it, but the instructing here is like he's instructing a machine to do something. Okay. Now, conversing is something else. Conversing is a conceptual model where the system goes into an interaction with the user. Okay. This is something many companies working in the support, user support area will try to do with their automated voice replies. So they would go into a conversation with you by, having a pre-recorded message by a human, like what would you like to, what option would you like to do? Press number 1 to do this, press number 2 to do this, press number 3 to do that. And when you press number 3, they will tell you, okay, welcome to the support department. What would you like to do? You can press so and so and so and so. And it goes like this. You're going into a conversation with the user. The user understands that. And the user is not stupid. He knows that he's talking to a machine, okay? Unless he has never seen this before. But he knows it's a machine, okay? But the point is, this conversing mental conceptual model is something the users are used to, okay? He must have at one point in his life went to a shop and asked for the support, and he went into a similar dialogue, more or less. So, or even saw it in the movie. So it's understandable, what he's engaging in. Okay, he says something, he hears the other side, he make a decision and continue on. Now, there is another conceptual model which is built on manipulating and navigating the user interface. Okay, in this case, the user would manipulate an object, and the user is supposed to perform actions that is similar, if you're trying to invoke the conceptual model here, is similar to what he does with parallel objects in the actual world. For example, in Windows and Mac, if you'd like to delete a file, you would drag it to the trash bin. That's exactly what you do in real life. Okay, so here what we are relying on, you don't even need anyone to take a course in, even if he has never ever seen a computer before. Okay, he doesn't need to take a course to understand how to delete a file. In real life, he takes a piece of paper and throws it in the trash can. On Windows and Mac, he drags the file with the mouse and put it in the trash can. Okay, we are basically relying on the user conceptual model of manipulating and navigating, or specifically here, manipulating paper. Okay. Now, the fourth conceptual model is based on exploring and browsing. Okay, this is what you do, and you started doing that since your childhood. Whenever you're given a map, you keep looking at it and folding it and unfolding it, and perhaps holding a magnifying glass and looking at the city names and the roads and so on. Now, this is a conceptual model that is based on the activity of exploring. Okay, and this is exactly what mapping applications like Google Map is trying to give the user. If you notice, there's no help in these applications. You open the application and here is a map. The user does not need any help, does not need to read documentation. He knows this is a map, and he knows he can move it to the right and the left, up and down, and he will quickly discover that he can open his fingers and close them to zoom in and zoom out. Okay, there's no map. There's no documentation needed here, because it's relying on the user stored mental model related to, or conceptual model related to exploring and browsing as well. It comes in the packaging. Now, so we said there are conceptual models based on activities, and there are also conceptual models based on objects. When the user sees an object, he immediately recognizes what this is, what it can be done with it. Okay, for example, if you see a dictionary, you know what it's used for. If you see a credit card, you know what this is used for. If you see a light, you know what is this used for. Okay, now you have stored how this thing abstractly look like glasses, for example. You don't have to look at every or memorize every glass design to figure out that a specific object you're looking at now is a glass. Okay, because you've stored the abstract idea of sunglasses or of glasses in your in your memory as a conceptual model. Associated with it is the functionality and the layout and the form and the texture and the look and the geometric proportions and so on. Okay, where do we see this in the user interface? In the icon design. Icon designs are basically trying to invoke object-based conceptual models. So when you look at the icon, you know exactly what this is for. You look at the icon and it looks like a printer, you know you can print by clicking on it. Okay, you look at the icon and it looks like a color palette, you know that you can draw something, and it goes like this. Okay, so The reason why icons are successful in the user interface is because how close they actually map to a specific object conceptual model. Now I will show you here, the most classical example of invoking the right conceptual model. What you're looking at the bottom of the screen is a screen capture from an application called VisiCalc. Now VisiCalc is, would go into any museum of the history of computer science and engineering, because it did something no one else did it before it. VisiCalc, if you actually look close to it, it looks almost like Excel but in black and white, and it is actually the first version of a spreadsheet. Now this was extremely popular when it appeared, because before it all the big companies like IBM and DEC and so on were selling accounting software, but the accounting software didn't look anything like the accountant ledgers and balance sheets and other financial statements. Okay, accounting software before VisiCalc was basically form-based, where you open a form, you get some fields, you fill in the fields, and then you click on another button, you get more forms, you fill in the forms, and finally you click generate, say, balance sheet, generate income statement, and so on. Now this guy comes, unfortunately I cannot recall his name now. This guy comes and says, no, I'm not going to build the software like that. It's not going to be form-based. It's not going to be like any other piece of software. I'm going to build what the accountants use in their daily work, which is an accountant ledger. An accountant ledger is basically a book that more or less looks like a spreadsheet, okay? Except the accountant used to do the calculations by hand, or using perhaps a calculator. So what he did, he laid out the user interface exactly in the same way that an accountant ledger would look like. The reason why this became a hit, and he made millions of dollars from this application, because no one else did it that way before. IBM and DEC and SAP, SAP, and all these companies were doing something else. They were doing form-based user interfaces. Form-based means you get a text field, like or a set of text fields, like what you see when you register on a website, or you enter your details like your credit card and so on. So what this guy did is he laid out the software in exactly the same way as the ledger, and what he actually did by that, he obviously this is not a real ledger, so you could call it, it's a metaphorical ledger. It embodies the idea of a ledger, but it's not a real ledger. This isn't software, and it's all being manipulated by a program. Okay, but the use of the ledger metaphorically here was extremely important, because basically it enabled him to invoke the conceptual model of the ledger and other financial statements used by accountants. So the learnability here is zero. If an accountant has been working as an accountant, and he know about his books, and he know about his income statement, financial statements, and so on, and balance sheet and cash flow statements and so on, he will use this software without actually opening any documentation. He will just start it right away, plugging in the numbers, and the values gets computed at the bottom. Okay. So the reason why this was successful, the application relies on the conceptual model around, the ledger and other financial statements. Okay. So this became a lesson for interface designers. Again, I probably already guessed this. You can see the video how old it is. It's many years back. I would assume now it's by 40. It's almost 40 years now, since this was introduced. I think it was in the late. A little less actually. I think it was. It should be by now 35 years, because it was introduced somewhere like 1982 or 1984. Okay. Now, so let me read this. The advantage of a metaphor is that you're using a conceptual model that the user already has experience with, so the user can quickly recognize what he's dealing with. Okay. And this became an instant success. And because of this, a lot of things changed in the software industry. Because of the success of VisiCalc. Okay. Now, so if you use the right conceptual model, it's familiar to the user, it's simpler to use, the user will be accurate using it, he will not make mistakes because he has been trained on the other real thing that he has stored in his memory before, and obviously it's more efficient because you will save the learning time, and whatever skill he has, it will be transferred to the software. Now, here is another example of using metaphors, which is the desktop interface. What we call nowadays desktop interfaces like Windows and Mac is really using the metaphor of a desktop. It's not obviously a physical desktop in any way, and it's not even using the same objects that you see on the typical desktop, even with the same shape. So the folder icon that on any desktop, whether it's the current Windows or Mac, doesn't exactly look like a physical folder, but it's metaphorically it's a metaphoric folder. Okay, it takes the idea of a folder, somehow, and simplify it, and it becomes more of a metaphor than a real thing. Okay, now you gotta learn this the story of the desktop, because this is another very interesting example of early user interface design. Now, we owe current desktop designs to a company called Xerox. Xerox is if you know, is a photocopying machine company, and they make photocopy machines to basically make copies of paper. Now, Xerox realized that the computers are going to change the world back in 1970s, and they said, okay, we are in the photocopying business, and we will run out of business because of computers, because people will not need to print as many paper as they used to, because now we have hard disks. So they said, okay, well, let's build a research lab that will give us insight into what's happening inside the computer industry and the software industry, so that perhaps we can take advantage of what's going on. So they built this Xerox PARC lab, okay, in I believe it's in California, and it was supposed to be researching advanced interfaces. That was back in 1970s. Now, one of the researchers there came up with the idea of using the metaphor of a desktop to build an interface instead of command line. Remember, then the only interface that was people were using was command line. So you log into a Linux shell terminal, and you type commands like ls, and and if you would like to write a document, you type vi, and you get the vi editor or Emacs and so on. So he built something that looks like a physical desktop, and that's what you see on the right side. This is the first ever desktop computer. This is using the idea of a desktop, but it's not obviously a real desktop, either physically or even representation wise. Everything is simplified. Instead of a folder, as I mentioned, it becomes like a little square. And instead of a file, it becomes another square with a bent edge, so it looks like actually it's a piece of paper. Okay. Now, for your information, many famous computer scientists and businessmen did internships in Xerox PARC, including Steve Jobs himself. So, and a lot of people who went and worked with Microsoft when it was just a small company made up of 10 people, many of them actually passed also through Xerox PARC or saw Xerox PARC work. Okay, so it wasn't really an innovation of Bill Gates or Steve Jobs. It was really Xerox PARC. Okay, now this is another example of using conceptual models, as I mentioned. Okay, and obviously this was enhanced a lot later on, as you know. Here is another example of using conceptual models. Okay, if you're familiar with the Mac interface, this is the iBook. So this looks like bookshelves, and it will invoke immediately in the user mind the conceptual model of a library. Okay, and the same thing we have in the desktop, as I mentioned before. Now, here is another example of using metaphors. Historically, order forms, before the internet, there used to be something called order catalogs. You get a catalog, like from a company like Macy's or Walmart and so on. You get this catalog that has product pictures, and then under each product picture you have a product ID. And then at the end of the catalog, you got these order forms. You cut one and you write down the product IDs and the number of items you would like to buy from each product, and you send it via mail, and then you get the product later on in the mail. Okay. Now, when in the very, very early days of the internet, people were trying to do a similar interface. Okay, so you go into a product page or online in a website, in an e-commerce website, and you click add to cart, and what you get is actually something that looks on the like what you see on the right side. Okay, more of here's the product ID, here's the product color, here's the product number, here's the product serial code, and tell us how many items you would like to take from this product. So they were basically copying, the order form. But this order form was not popular to everyone. If you have done ordering in the mail, you would have seen it. But if you haven't been into ordering, or you haven't practiced, ordering items through the mail, then all of this doesn't make any sense to you. But what makes more sense to you is the shopping cart, because everyone goes to a supermarket, and there is always these carts that you put your items in. Okay, so another example of invoking the right, or a better conceptual model is the model of the shopping cart. Okay, much better than the order form. Okay, when you click on an item, you see it flying into the shopping cart, so okay, now I've added to my shopping cart. Okay, but when you click on an item and then you're taken to a screen that tells you, okay, this is my order form, you have to click submit. It's not exactly what everyone is accustomed to. Now you still have to go at the end through a checkout process, even if you use a shopping cart. But the notion of using a shopping cart makes it much easier for the user to understand what is this all about. Okay, that he's adding items he can buy later on. Now, the problem here, the pitfall with using metaphors or using ideas from the physical world to embed them in software to try to activate a conceptual model, is that you have to be careful with your choices, because what we are after is decreasing learnability to almost zero. What we're also after is efficiency and effectiveness. Okay, we are not designing an interface for internment purposes. We would typically design an interface so that the user can get his job done, and if he's going to get his job done, it has to be done quickly. If there's a chance to do it quicker, then you do it quicker. Okay, now let's look at these two examples. On the left, you see an iPhone, and the dial screen has been changed to simulate or work like the dial circle that existed in old phones. If you have seen this in the movies, the way they worked is because these were analog phones, like the one I'm referring to, the black phone at the bottom. These were analog phones, and the phone should send a different tone for every one of the numbers. And the way this works is you rotate the phone some distance around the center, and the rotation sends a different tone, because you are basically playing with the analog electronics inside. That will send a different tone on the wire with every time you rotate it. So when you rotate the 1, and then you release your finger, so it goes rrr, okay, and then you rotate the 9, so it goes rrr, it goes a little bit longer. Okay, and this is how you generate different tones. Okay, it's not the sound of the rotating disc, it's actually the electronics inside the phone that will send a different tone. Okay, now if you go to an iPhone, yes, when I look at this, I will immediately recognize this is a dial pad. Okay, but there is a faster choice, there is a faster design, and the faster design is just to lay out the buttons in front of the user so he can press on them. Okay, why do I have to force the user to put his finger inside the the circle that has the number, and then rotate this disc, and then wait for the disc to return back, and hearing the same sound as you've probably seen in old movies, back and going back. Okay, that's a waste of time. Okay, so this is not a good use of metaphors in any way. Okay, when you use it, you have to keep in mind, you're using it to invoke a certain conceptual model in the user brain, but you have to make sure that it's efficient and it's effective. Okay, it's efficient means it doesn't take more time than what it needs to. Okay, and it's effective means it achieves the job. Now let's look at also another usage of a metaphor that is not entirely successful. On the right side, what you see at the bottom, there is this guy who is actually testing if the plane is perfectly balanced. What he's holding is something called a water ruler. I think in Arabic they call it mastaret maya or mizan, and what's actually is he's looking at the little green area which also appears inside the cell phone. He got typically a liquid or an oil. I think it's a liquid with an oil drop, and if the oil drop is exactly in the center, then that means that the surface is 100% not inclined. It's a plain surface with no inclination. Okay, so you can adjust the inclination of a surface by monitoring where is the oil bubble which is in the center of the yellow bar. Okay, Now this is obviously a manual tool. It's a very old tool. It's a relatively smart idea. It worked for many generations, perhaps even centuries. But let's go now and talk about this reincarnation of it inside the cell phone. Now inside the cell phone you have a lot of sensors, including gyroscopes, accelerometers, inclinometers to measure inclination, and so on. So you can actually display accurately the angle of inclination of the surface the cell phone is sitting on. As you see here, it says -45. Okay. Now, so for what purpose would you display the yellow bar at the top? Well, you already are displaying the number -45. This is even more accurate than the oil bubble in a liquid. Okay. So yeah, you will invoke the metaphor, but here the usage is completely absent. Okay. Anyone who is using cell phones would just look at the number, and it's more accurate than the light, than the oil bubble or the oil drop. Okay, so this is basically an abuse of screen real estate. Okay, and it's not effective. It's not going to be used. Okay, what people will look at is the actual number. Okay, so when you take a physical phenomena or a physical device in the real world and you put it in software, make sure that you are activating the right conceptual model, and your interaction is still efficient, unlike the cell phone example, and effective, unlike the ruler example here. So the takeaway: utilizing an appropriate conceptual or mental model via a metaphor in an interface increases efficiency and effectiveness. Okay, but it has to be, as I mentioned, an appropriate one. Now, also related to that is the display of images and icons. Okay, there's a lot of things that happen in the human brain that is quite subconsciously to you. Okay, so you don't really feel it, but it does play a role in how you react to everything you see. For example, if you would like to invite the user to encourage interaction, that the user responds to what is being displayed, and make sure that the icons and images are encouraging the interaction. Okay, there has been an experiment I'm reporting here by Elder and Krishna. I've linked to you the paper that was doing this, that even displaying a cup with the wrong orientation affects the interaction. Okay, so this has a lot of implications on icon design. People who study icon design will talk a lot about this, but I'm just going to mention it here as to give you an understanding that whatever that gets displayed to the user either is inviting or discouraging in an interaction. Okay, the same thing here. If you'd like to invite people to eat, then there has to be a spoon. Okay, it sounds a little bit naive, but it's not. This is how we our brain work all the time. Okay, either you're engaging him or her in an interaction, or you're not. So the correct version here is a dish with a spoon, not without a spoon. Okay, and I'm just showing you simple ideas, but apply that anywhere in an interface. Okay, apply anywhere you choose icons. When you choose icons, then make sure that the icons are inviting the interaction. Okay. Now we come to the following idea, the notion of affordness. Okay. The takeaway from the previous two slides is that when you design an object, physical or virtual, it has to have the right affordness. Okay. There's a very important design concept called form implies function. That when you look at an item, when you look at or a picture of an item, or when you look at an icon, or when you look at an interface, it has to have the affordness of usage. Okay? In other words, you don't need to have a PhD in artificial intelligence to know what is the object in front of you is for, or how to use what's in front of you. Okay? So when you inspect any object, whether it's virtual or object or physical, there has to be clues that tells the user, this is how I work. Okay? Now I always like to rant about this, so I'm going to rant about this. If you have been in any public place, Actually, no, let me be more specific. Now, in the university, probably in any university, in any lecture hall, there is a unit to control the air condition, and the norm is to have a knob. You switch it from the lowest temperature to the highest temperature, which kind of makes sense because that's really the only thing you need to control in an air condition in a big hall. You turn it on, you turn it off, you turn it to the right, turn it to the left. Okay. Now, in our university, for some weird reason, the company that actually installed the air conditions, I believe it's a German company, but I can't recall its name, changed the interface of the air condition unit from being a knob to an LCD. So when you walk to the LCD, you look and there is nothing you click on because the LCD is switched off to do power saving. But why would you need an LCD to control the temperature? Okay, the affordness of turning it on and turning it off, or to the right, rotate left, rotate right, is enough for anyone, even if he doesn't know how to read and write, to understand this will control the temperature. Because anyone, even in remote parts of civilization, knows that turning a knob on and off will switch on the heat on and off, in a stove or on even a barbecue device. Okay, so this notion is turning knobs on or rotating it to the left and to the right is associated with increasing and decreasing temperature. Okay, but when you walk in and you see an LCD, and it's like you're puzzled. What is the affordance here? There's no affordance. The only affordance to an LCD is to click on it, and then you get this menu that now you have to navigate and learn to figure out how you actually control the temperature. Okay, so it's a bad design from the first place because it didn't respect the notion of affordance. That the historical object for controlling temperature was this knob, and it has perfect affordance. You know how to rotate it because it looks like a circle, so you're going to rotate it. Okay, you're not going to pull it from the wall, for example. Okay, so anyway, this is my rant. So affordance is very important. Okay, and it becomes extremely important with physical devices. And as you will discover actually in this course, you can brainstorm and design a physical device that will do something. This is actually something that you can do in the project. So you have to think a lot about the affordance. Okay, and this is what I write in the bottom bullet: that affordance of an object invoke the related mental model of how to operate it. Okay. Now, here is an example in this screenshot of a violation of affordance, and it exists in almost all over the world. Okay. Now, when you hear the word pull, to pull something, you have to put your hand inside that and pull it towards you. But when you're told push, you don't put your hand inside it and push, because that will take your body forward. What you do is you rest your hand on the surface and then push. So the image on the left where it says push, the handle has wrong affordance. It's not supposed to be like this. It's supposed to be a flat piece of metal or whatever, and the user would rest the inside of his hand, the palm, and just push. Okay, this is as simple, an example as I could get that shows the difference between a well-thought design that includes affordance or into consideration versus just a copycat or an unthought of design. So the takeaway here is that you design an object, physical and virtual, with the right affordance, because again, form implies function. Okay, and you can watch this optional video. It's quite entertaining. Now here is another example of affordance. What you see on the left is a teapot. Do you need actually to be educated to learn how to use a teapot? Actually, teapots were invented, I believe, by the Chinese thousands of years ago. Okay, and I don't think that you needed to learn how to write Chinese as a Chinese person, to thousands of years ago, to know how to use a teapot. I mean, it has a hole in the top which you can expose by taking the cover, and it has a handle on one side, and it has an outlet on the other side. So for sure you know where to put the water from, where to put the tea leaves from, and how to hold it, and what's going to happen if it's tilted. The water is going to come out. Okay, it doesn't require intelligence to actually use a teapot. In fact, probably monkeys could use teapots. Okay. Now, if you look at the right side, the problem with this, you keep looking at it, it's just a wrong affordness. There's no way you can hold it and try to pour the tea without actually getting your hand burned. Okay. So left is right affordness, has been around for perhaps 4,000 or 5,000 years. Right is wrong affordness. Okay. Next, we're going to look at the topic of attention. Okay, this is again cognitive psychology stuff, but also very important to us because we are going to use that in interface design. So when you're asked to pay attention to a topic, like for example listening to this lecture, this attention has many types. There are two broad types first, focal versus peripheral. Focal means it's in front of you. Peripheral means it's in your peripheral vision, which I've described earlier when we talked about the eye. Now, focal is divided further to focused plus divided. And we are going to split focus to three types: sustained, selective, and alternating. Okay? So let's start talking about attention and see implications for user interface design. Now, the first one we're going to look at is what's called sustained attention, which is a type of a focal attention. Now, in sustained attention, it's the ability to focus on one specific task for a continuous amount of time without being distracted. Okay? So if you're listening to a lecture, you go into what's called a sustained attention mode. Okay? Now, in sustained attention, you're trying to focus on one task and not one task, and you keep focusing on it. Okay? Now, how do you support sustained attention in a GUI? You support sustained attention by preventing distractions, which goes back to the interference issue we discussed earlier. Okay? This is why in all successful applications, you will see that the main task this application is supporting, like for example WinWord, supporting writing. You write documents in WinWord. The majority of the screen is allocated to the main task to enable you to go into sustained attention mode. Okay? In fact, there is even a better editor than Word. It's called JDarkroom. Okay, it's a great tool. I sometimes use it because when you open it, you get a blank screen and a cursor. Nothing else. No menus. Okay, nothing. No food bar. Nothing. Just blank screen and a cursor. It's perfect for sustained attention because if you don't want to be interrupted, then don't have anything in front of you except what you're working on. Okay, so you support sustained attention by dedicating the majority of the screen real estate to the main task. Okay, that's number one. Number two, you avoid interrupting the user. Now that's provided that the application you are building is actually, it requires sustained attention. Not all applications are like this, by the way. Okay, the user might open an application and put it in the background, like for example downloading files. Okay, so this is not an application that requires sustained attention. When we talk about sustained attention, I mean a task that the user is going to go on, use it for an extended period of time, and he's doing a mental effort that should not be interrupted. Okay, not a short burst of interaction and then put it in the background. Now there is another type of attention called selective attention. Selective attention is the ability to select from many factors or user interface stimulus and to focus on only the one that you want while filtering out other distractions. Okay? So selective attention means you're going to select among a set of displayed items. And the question is, which one you select. When you're actually trying to select, you're doing selective attention. Okay, so it's different from sustained because you have a number of options in front of you. Now, how you support selective attention in the GUI? Okay, you display non-overlapping user interface elements in different visible locations to enable the user to quickly select what he wants. Okay, so again, I'm going to read it. Say display non-overlapping user interface elements. They have to be non-overlapping because you don't want the user to spend time trying to set them apart to be able to select from them. Okay. Now, I will show you one change Microsoft did that actually enhanced a lot the selective attention process, which means it decreased its time, because here you want to decrease the amount of time the user is doing in selective attention. Okay, here is the historical menu that Microsoft had very classical. You open a menu, you got this linear menu, and then you got submenus, and from the submenus you got submenus, and so on. Okay. Now every time you open one of these menus, you're going to scan with your eyes through the different options because you want to pick one of them. Okay. Now this is what Microsoft did later on. They introduced the ribbon, which I have discussed briefly about before when I was talking about the gestalts. Now, what they did in the ribbon is that they flattened all their menus. They had like a huge hierarchy of nested menus. They flattened it and they put it all in front of the user. Okay? This speeds up the selective attention process because the user does not have to go through a process of clicking through submenus, and scanning those submenus when everyone opens to actually decide where to go next. So all that was thrown, and they just laid out everything in front of the user, and the user can change the tab content by clicking on the labels at the top: menus, home, insert, page layout, references, and so on. So here is an example of a research work that redesigned the whole desktop idea, the whole desktop, to support selectively attending to specific time intervals. So in this work, which I linked the prototype video on YouTube, as you see at the bottom, when you open your desktop, what you see is a timeline, and in the timeline there are events, and you first focus on an event by paying attention or selectively being attentive to a specific event using the timeline, and then you dig down and you start seeing the files and folders and images and videos associated with this specific event. So all your life is basically a series of events, and every event has files associated with it. So if you would like to go and see, say, your school reunion that was done in last winter, you have to go through the timeline selectively, attending to the specific time interval you're interested in, and then you click on there, and then you see the details of that timeline, or that event in the timeline, and then later on you will see the attachments, which is the images and videos you took through in your school reunion. Okay, so this is an interface that kind of thinks of a desktop in a completely different way. Obviously, this is a research project. This is not in production, but it is based on the idea of enhancing selective attention in your content. Okay, so if you look up for content, you look it by the timeline. Okay, and you selectively attend to a specific time interval on the timeline. Now, the next type of attention we're going to look at is what's called alternating attention. Now, in alternating attention, it's the ability to switch your focus back and forth between tasks that require different cognitive demands. Okay. Now, this is actually what most of you subconsciously would do when you're studying, when you open the TV or open YouTube or open Netflix, okay, or open the radio even while you're actually studying. Now, this notion of alternating your attention between what you're studying and what you're watching on YouTube or Netflix or whatever is not a good idea, actually, okay, because it will take you more time to study, because you are switching your attention back and forth, and this is what alternating attention is all about. Okay, so what your parents told you when you're young, that when you're studying, don't open TV and don't listen to the radio and so on, this comes obviously from collective human experience, that you're just going to slow down. Okay, if you're enjoying it, well, that's up to you, but you can actually study faster and just move on. Anyways, so this is alternating attention, what you're doing. Okay, you are going to switch your focus back and forth between the tasks, and this is a property of alternating attention. Okay, now where do you see that in an interface? You must have seen it. If you have Windows, you have this shortcut Alt-Tab that takes you between different applications. So this is actually alternating attention, okay, when you switch from one application to another. Now, generally, you want to decrease the time the user spends in alternating attention mode, okay, because he's alternating his attention back and forth between applications, and all of them are of equal importance to him or her, so you want the switch to be as short as possible. This is what Microsoft did by changing what you see when you press Alt-Tab. Historically, it used to be the image on the left, And that has a problem, which is if you open several instances of the same application, let's say Firefox here, and you keep going back and forth, you don't know which Firefox actually you want to open now. So you spend the time going back and forth between instances of Firefox. Okay. On the right side, they enhance that by, instead of displaying the icon, they display a miniature screenshot of the actual window. So when you're actually alternating between them, you know quickly which one to jump to. So here the goal is to decrease the amount of time that you spend between the alternating applications or the application that you're alternating between. Okay. Now, another thing you should do in an interface to enhance alternating attention is to enable the sharing of data between applications as smooth and as fast as possible. Okay, because if the user is switching his focus back and forth between two or more applications, most likely he would like to share content between those applications, and consequently, if you speed up that is a good idea, because the user will not waste time trying to copy data from one location to another. Next, we're going to go to divided attention. Now, divided attention is different from alternating. Divided attention is the ability to process two or more responses or react to two or more different demands simultaneously. By the way, while you're studying, that's why again it's a bad idea. You're either going into alternating attention when you leave what you're studying and look at the YouTube channel that you have opened, or you could go into divided attention mode, which is even worse than alternating attention. Now, divided attention, you will process both input streams, the textbook that you're reading using your eyes, and the YouTube channel using your ears. You will track the sound or what's happening in the movie or what's happening on the program that you're watching on YouTube at the same time. This is called divided attention. It's not alternating. Okay. What divided attention entails is that you're allocating the resources in your brain to two or more input streams, and that means that you are allocating to each one of them, if you'd like, half the processing power of your brain. Okay, so if I'm studying and reading from a textbook and also listening to YouTube at the same time, my brain will be doing both at the same time, listening to YouTube and reading. So if I think of my brain as a processor, now it has to run these two things or understand these two things, okay, at the same time. So I will go back and forth, which means the processing of the text I'm reading from the book is going to be a little bit delayed because of the input stream coming to me through my ears, because I'm following a YouTube movie or a YouTube news channel. Okay, so divided attention was a source of debate among cognitive psychologists for a while, until a number of experiments has proven that divided attention is possible in the human brain. Okay, divided attention is important because this is really what we call multitasking. Okay, alternating attention is not necessarily multitasking. You could alternate between different applications, but in each time you go to an application, you're working on it all the time. But with divided attention, we're talking about working on two or more applications at the same time, or two or more input streams at the same time. A very classical experiment that kind of proved that divided attention exists is called the Stroop experiment. Very interesting experiment. Here is how this works. You get a number of participants. You can try this with your family at home, since probably it's not advisable that you get your friends at home to, in the current situation, to do an experiment on them. So the Stroop effect goes like this. Again, you can try this at home. Okay, what you will do is you will ask someone to tell you the color of the word, and you have three variations. In the first variation, the word and the color match, like red is in red, green is in green, which is the image at the left, and blue is in blue, and yellow is in yellow, and pink is in pink, and so on, and white is in white. So it's the name of the color matches the color. On the right side, you see the red written in green, and the green written in yellow, and the blue written in white, and so on. Okay, and at the bottom you see words that are not names of colors. So usually this would be, these three conditions will be giving names in the psychology literature. The one at the left is going to be called congruent, which means that the name of the color and the color agree, the one on the right is going to be called incongruent because the name of the color and the color disagree, and the one at the bottom will be called neutral. Now, interestingly, it has always been found, and this has been repeated in many variations and in many labs around the world. You can even do it at your home and you will find the same result, is that if you measure the time it takes or count the number of errors it takes to do the three conditions, congruent, incongruent, and neutral, you will notice that the incongruent condition will have more errors and the response will be delayed. In the incongruent condition, when you ask the participant in your experiment to tell you the color of the world, they will also read the name of the color. So if you tell someone, tell me this color, and you point at the top row where it says blue and it's written in white, they will look at it. Even though the color is white, some of them will do a mistake and tell you it's blue, and other ones will tell you at the end it's white, but they're going to take more time compared to the one on the left where the white is written in white. The response will be much faster. This has been shown this shows that when the user is looking, or the participant is looking at the incongruent condition, which is the one on the right, there is interference between reading the text and naming the color. And if this was done one after the other, there shouldn't have been a problem. The only explanation for why the user response will be delayed in the incongruent condition is that the user was actually reading the word and thinking of the color at the same time. And this is a proof that humans can do divided attention, because that means at the same time they were processing two input streams, the color and the word. Okay, and if they were done serially, if this was done serially, you wouldn't have faced an issue, because you would focus on naming the color and then you would read the word. But that doesn't happen this way. For all humans, it's subconsciously they will do both inputs at the same time, which means they're doing divided attention. They were capable of doing divided attention. Now, this has been utilized in interfaces. For example, this research work from many years back that nowadays exists in many drawing applications, where you see transparent user interface controls, and the user will still be able to use the application because they will look at the user interface control, and they will also look at the object being manipulated at the background in the same time and understand the effect of the interaction, which is, for example, as you see at the second image from the left, coloring the segment with green, okay? Or you see at the far right, applying a lens to see a magnified version of the image in the background, okay? So this is something now that's standard in user interfaces, and it comes from our ability to do divided attention. Here is another example of utilizing transparency, which is related to divided attention. This tries to solve the problem, and again this is coming from research, trying to solve the problem of having rectangular windows, which is a problem by itself because we have a lot of wasted screen real estate. For example, if you look at the image, the folder at the left, the window at the back, which is in black, is almost completely hidden, even though at the front, the window at the front has a lot of empty space. So the researcher tried to solve this by using transparency to show you a content of what appears in the window at the back. Now, this is possible because we can do divided attention. You can look at both of them and consume both of them at the same time. Now, here is another example again of divided attention. At least part of it, even though there are other kinds of attention that appears here. This is another research work in which the user overlaid a projector image on the top of a frame where the frame has a hole, and in the hole there is an LCD screen. What the user does is he can manipulate, for example, a map by displaying it on the projector, so it gets displayed in the big golden frame, and the areas that the user would like to display in high resolution will drag it to the LCD screen. So two displays act as one with high resolution, which is the LCD screen, and a lower resolution, which is the projector. Now, when you're looking at the LCD screen, you're seeing the map in context, or you're seeing what is displayed on the LCD screen in context of the big picture, and you're consuming both when you're actually looking at them. You're not just looking at one and ignoring the other, unless you bring your face very close to the LCD screen so you don't see what is the output of the projector. Okay. So when you're sitting at an arm's length, you're actually looking at both at the same time, and you will process both. And again, this is a utilization of divided attention. Now we come to the topic of peripheral attention, which is being aware of changes in the periphery. And we have mentioned this before when I talked about vision. We have an ability to see changes in our periphery because of the existence of the rods. Now, consequently, we are aware of our environment at the periphery, and user interfaces has tried to make use of this fact to communicate information to the user. So first, let's define the peripheral. Okay, the focal vision, or focus attention, if you'd like, all occurs with what's in front of you within 60 degrees from your nose, 30 to the right, 30 to the left. Peripheral vision starts afterwards and extends all the way to the side, but the difference is part of it is done with both eyes and part of it is done with one eye. So you have monocular right eye range and the monocular left eye range, and that you're seeing only with your right eye, and the other one you're seeing only with your left eye. Okay, and you also have a very short or very small angle where you can see when you rotate your eyeball all the way towards the right or the left. Now, peripheral vision has been used, as I mentioned, in HCI because it is interesting as an input channel, because we already have taken the focal vision towards the LCD screen and what's displayed on the LCD screen in front of the user. And if we would like to communicate information to the user in the focal vision part, then we are going to interrupt whatever he's doing, and we said this is not a good idea, that to interrupt the user. So what remains for us as an area to work with is the peripheral vision, and there has been many research works that tries to do this. This is an example of that, which comes from Microsoft many years back, and it has been an influence on many other applications that appears up till today, including Facebook Messenger and so on. The idea is to display important information to the user as notifications or changes of colors, and as dots, as shades of gray, if you like, even at the periphery of the screen. Okay, so when the user is working in a sustained attention mode and a message quickly appears and disappears at the bottom of the screen, as long as it's in the periphery, then the user will not be interrupted. Okay, but if you obviously put the message in the center of the screen and the user is forced to read it, that's definitely an interruption. Now, Microsoft even goes nowadays, as I mentioned before in today's lecture, even further away from this. There is a no interruption mode nowadays in Windows, or a silent mode, I believe. I'm not sure what it is called. I tend to forget. Now, in that mode, you will get no notifications at all. Okay, but peripheral notifications could be acceptable in the sense they will not interfere with the user, okay, because the user will see them using his peripheral vision. That's if they're really in the periphery, so this has to do with the screen size as well. The bigger the screen size, the more guaranteed that actually the displayed message is in the periphery. But if you get a very small screen like 14-inch, there is no periphery there because it's all in the focal vision of the user. Because as I mentioned, think of your nose and you got 60 degrees, 30 to the right and 30 to the left. So you can measure it from where you sit. If you sit, with your back straight and you're at an arm's length from the screen, you can measure where that 30 is. Okay, so if your screen is big enough, then you can start to display notifications on the periphery, and the user will see it in the periphery. Now here is another example, very entertaining one, from a lab in Canada. And what they do is they attach objects to the screen, and those objects are programmable, and they move up and down to signify events to the user. So they provide peripheral information channel to the user without the user paying or directing his attention to them. Okay. Now this whole idea has taken off for a while in SCI. There has been a number of research works related to it, and there's even some products. I believe I will show you one in the next slide. They are called all ambient interfaces, which are interfaces in the periphery. So you try to communicate information to the user through the periphery, and they extend beyond devices that you can attach to the screen. One of the earliest works by MIT Media Lab is a fountain that exists outside the office of a number of researchers, and they programmed the fountain to tell the prices of stocks. So you'd be sitting working inside the desk, and when you hear the fountain water increasing its volume, so it's spitting water up at a higher distance, so you can hear it. This means the prices of certain stocks are going up, and when the fountain sound completely disappears, this means that the prices are going down. Okay, so the notion of ambient interfaces, is interesting by themselves, because you communicate information to the user without the user doing any effort, and it's communicated through the periphery, so you're not going to interfere with the user as well. This is the example I was telling you about. This is actually a product you can buy. It's called the Dyno. I'm not sure if it's still around or not, but the last time I checked was last year, and it was around. You can buy this egg-looking shape, you put it on your desktop, you connect it through USB, and you program it to turn on and off with certain light colors, certain colors, whenever some events happen. Okay, so if there's an emergency, then it will turn red, and if someone would like to talk to you on the phone, it's going to be blue, and so on. Okay, if there's a meeting coming up, it will be green. So while you're working, you notice from the periphery that the color is changing, but you're not actively seeking the information, which is an advantage. Now, peripheral awareness also has been used in public displays. In the future we will see in malls and in sporting clubs these huge screens that are basically LCDs with a computer behind them, and you really need to rethink the whole interface, because this is not an individual screen. This is a screen in a public space. There will be many people passing by it. So in this research, actually, the researcher suggests using peripheral awareness to attract the user to the fact that there is a message for him or her that he could see and check using the screen. So when the user is passing by, a vertical segment with certain color will track the user movement. So you're walking by and you see something walking beside you. The bar is walking along you, so you know that it looks like this is a message for you. Obviously, if at the first instance you're doing that, you will think it's an accident. But if you keep walking, and this is a big display, maybe like 5 or 6 meters in width, after a meter or two, you will realize actually it's tracking you. So when you face towards it, it will open up, it will increase its width. So you know, okay, this is for you, it's not for anyone else. Okay? So, again, this is using what? Using your peripheral vision. Because when you walk by these devices, you will not be facing them, they will be on your side. So you're seeing them from the periphery. So, the takeaway here is that utilize peripheral attention when you want to communicate change in status of some information source in a salient, non-intrusive way. Okay. Now, the last topic I will conclude today's lecture with is spatial attention. Now, I have mentioned before that we have many types of attention. We have a very special type of attention called spatial attention. And we are doing that all the time. We're always paying attention to location of items or objects. It's part of how we do the encoding in our memory. Let's say, for example, you come to the university one day using your car, and you park it in the university parking space. You spent the whole day, it was a tiring day. By the time you're leaving, you don't remember where did you park your car. So you start thinking of items that were close to your car. For example, you parked the car under a tree. You have seen a specific security desk and you turned right after the desk. Okay? Or when you parked, you entered from the last gate, electronic gate entrance. So you start to associate locations of items in relation to each other. The same thing happens if you forget the location of your key at home. So you start thinking, okay, maybe I put it beside the fridge because I was drinking water from the fridge. Or maybe I put it in the balcony because my parents were sitting in the balcony when I came home. So I went and I talked to them and I left it on the table in the balcony. Okay? So you're thinking of locations. So it turns out that whenever we encode something into our memory, whenever we try to store anything into our memory, and there's lots of stuff getting stored in our long-term memory that will disappear later on because again the connections are weak. So when you're storing things, one of the cues that you always store is the location. Where is that? This is very important, okay? And we are really good in doing this notion of storing locations, to the point that it has been used by researchers in HCI to enable the user to work in a different way with an interface. So I will show you some research works that try to do that. Basically, utilize spatial awareness and spatial attention, which is tied to spatial memory, which is the storage of locations and objects and their locations in memory. So here is one classical example of that. If you ask anyone who uses Mac about the top menu, they will tell you they like it. And if you ask anyone who doesn't work with Mac but knows about Mac, will tell you if you ask what is the thing you don't like about Mac, they will tell you the top menu. So what's the story of the top menu? Well, first of all, if you don't have Mac, you don't know what I'm talking about. So let me tell you what is this. You see, in the Mac interface, the menu is fixed in the top bar that you see here in the screen. In the Windows interface, the menu for any program is part of the window or the frame of that program. So every program has its menu embedded inside it, inside the frame, the top thing in the frame. In Mac, the window does not have the menu. The menu is always at the top. So if you're not accustomed to seeing this, because you're not a Mac user, you will feel it's awkward, because when you open an application, the menu is hanging up there and the menu is not part of the window. But if you ask any Mac user, they love it. Now the reason why they love it is because it's actually faster to work with than anything else. In fact, it's so fast that the option that Windows has, which is to put the menu inside the frame, will always lose against this guy. Why? Because when you fix the menu at the top line in the screen, and since it's always there, always the word file appears in the same location, always the word edit appears in the same location. And these are the standard menus that you see in any application. So all applications will have file and edit and so on. When you're trying to reach for them, you're going to use your spatial memory to determine the location of the file. So the amount of effort you do to actually position the cursor from anywhere in the screen to the file label up there is minimal compared to what you do on Windows. Because in Windows you have to look, find the frame for the window, and then take your mouse inside that frame and slowly approach the file label to open the file menu. Okay? Over here it's super fast. And this is why they like it, by the way, because subconsciously this turns out to be super fast interaction. Okay? And the reverse actually happens. When a Mac user goes to the Windows platform and try to use it, they will go crazy about the menu not being at the top, because it takes them more time to actually open any one of those menu items. So this is a utilization of actually spatial memory. that you memorize the location, and you don't actually have to even look. You can just take the mouse there, and that means the interaction is super fast. Now here is another, actually even more interesting example. We have a problem with cell phones, as you know. The screen real estate is ridiculously small, and consequently you tap a lot on the screen to go anywhere inside your cell phone. So what the researcher here suggests is to organize content into virtual shelves that are accessible according to orientation from the user body. So top right, or the column towards the right, far right, is going to be, say, for PDFs, and beside it there is a column for images, and beside it there is a column for audio files, and so on. And they rely on the user spatial memory to train himself to remember spatially, means location-wise, where are each one of those columns that appears in the grid on the right image. The user quickly can put his hand in the right location in one of those cells in this grid to pick an item. And when he will pick it using his cell phones, and they use the cell phone sensors to actually figure out which cell the user is trying to place the phone in, and consequently the interface changes and will open the appropriate application for him. So for example, if he puts his cell in this, if he puts his cell phone in the cell for university pictures, he puts it there and take it back and look at the screen, and he will see a list of university pictures, or pictures taken in a university. Okay, so these are called virtual shelves, and they rely entirely on your spatial memory. Okay, you got to train yourself a little bit when you're using it for the first time, and this is what's mentioned in the research, but at the end you will become super fast with them. Now here is another also interesting application of spatial memory. We all have memorized, because we have used cell phones for a while, the layout of the keys. So what this researcher is doing, she is wearing actually a camera in her eyeglasses, and the camera tracks where the finger is. The phone is actually in her pocket. When she would like to dial a number, she doesn't actually have to extend her hand to the phone, get the phone out, log in, and then type in the number. The camera is tracking the finger, and the interface relies on the user's spatial memory to remember where is the 1 compared to the 2, compared to the 3, compared to the 4, compared to the 5, to the 6, to the 7, to the 8, to the 9, to the 0. So if you'd like to type a number like 011, you will just tap where these numbers would be on the screen if the screen was in your hand. So you go ahead and click on your palm, and the camera is tracking you. Once you're done with entering the numbers on your palm, the camera sends through Bluetooth to a software on the cell phone that will dial the number for you, and you have a Bluetooth headset, so you can start the conversation. Okay, so again, this relies entirely on the detection of location of items and the orientation in relation to your body.